Hi guys, David here with another science update. So today I want to talk about a super cool paper that recently came out in Science, and it's called Lightweight, Strong, Moldable Wood via Cell Wall Engineering as a Sustainable Structural Material. And to cut to the chase, what's cool about this paper is that through just a couple of simple processes, they were able to take wood and make it into a easily moldable material that has structural properties that means that it can probably compete head-to-head in a lot of advanced engineering applications with certain aluminum alloys. Specifically throughout the paper, they compare the mechanical properties of the wood structures that they make to 5052 aluminum alloy, which is an aluminum alloy primarily alloyed with magnesium and chromium, which is reported to be used for marine, aircraft, architectural, general sheet metal work, heat exchangers, fuel lines and tanks, flooring panels, streetlights, appliances, rivets, and wires. And also, it has exceptional corrosion resistance. So this is really a widely used aluminum alloy. And the thing about aluminum is that structural aluminum is known for its good specific strength, which is its specific strength is different than just its strength. That means it's strength per unit mass. And that's important for any application where weight matters. So steel is obviously stronger than aluminum, but aluminum is lightweight, which means that it actually is stronger than steel per unit mass. And that's important for something like aircraft, for instance, or a vehicle. So they start with regular hardwood, and they say we first used a common aqueous-based delignification process to remove 55% of the lignin and 67% of the hemicellulose. So basically, wood is composed mostly of cellulose, but it also has a lot of other components called lignin and hemicellulose, which basically are parts of the cell walls of the wood. And removing those components basically makes the wood a little bit more flexible. After that, they dry the wood, and then they re-swell it in what they're calling this water shock process. And we can see here that this is what it looks like. So basically we have, in this figure, we have a schematic of the cell walls structure of the starting hardwood. And you can see that there are vessels. This is kind of like a cross section, and you can see the lines themselves are the cell walls. So their vessels are these open spaces, and then there are fibers which add structural support. And this is what, down below, this is what the hardwood looks like before you do anything to it. And you can see they just broke it in half. It's showing that it's brittle. It's strong, but it's brittle. It can be broken. And then you have the shrunken wood. This is after they treat it with they do the delignification, and then they air dry it, and that causes it to shrink. And you can see that the vessels basically have collapsed, that the cell walls, which kind of had these smooth, rigid structure, are now wrinkly. They're able to be folded and molded. And just generally the whole thing is smaller. And you can see that this material is also brittle because you can see that it just broke easily. And then they do a water shock process, which is basically putting it in water for, I think, 3 minutes, and then it swells up again. And this new material is now moldable. And you can see this, they're actually molding it. And so let's look at a couple of videos to get a better sense of what that looks like. Okay, so this first video is the rapid water shock process sped up by 10 times. And you can see basically this is the wood. This is the wood that's been dried and delignified, and so it should have that kind of like crunched in structure, and overall it should be smaller. So when you see this, look for seeing it expand to some extent. And you can see it's in water, and it's hard to tell, but you can actually see it's actually expanding in this direction. And it's sped up 30 times, but the whole thing takes just about 3 minutes in total. Awesome. So in this video, sped up 3 times, we're going to see the moldable wood. So this is after the water shock process. And that is so trippy to see them do that with wood. And it looks just about the same after they're done unfolding it. And this video is showing more of the rolling and twisting that you can do. So up above we have the rolling, and he's gonna roll it up into like a really tight mat. It reminds me of a bamboo mat, but it's one piece of wood. As I'll talk about later in the paper, what's cool is that once you dry out the wood again after this step, it actually will maintain the shape that you put it in when you were manipulating it when it was in its moldable phase. So they can wind up with this nice roll at the end, or this hard and rigid twisted structure at the end. So while it's in its moldable state, as we saw from the videos, you can basically shape it in different ways. And you can see here that one of the common ways they looked at was actually to make this 3D molded wood corrugated structure that they could then put together with other sheets to make a honeycomb structure. And this is a common mechanical component. If you, for instance, for some applications, you'll see this honeycomb structure is going to be maybe under flooring or something like that, and it's known for its compression strength. In other words, you can press down really hard on it and it won't deform. In this part of the figure where we see these different radar plots, we're seeing basically a summary of the mechanical properties, or just the different properties rather, of 3D molded wood versus aluminum versus certain polymer composites, which might be competing with these materials as lightweight structural components. And the thing about a radar plot is it's a good way to look at many different properties at once. And you can see here the idea is that the materials are compared side by side, and if a particular material had the best properties all around, it would be completely filled out. So you can see, for instance, strength. You can see that 3D molded wood is strong, but it's not as strong as it could be, perhaps, compared to some standard. The specific stiffness is very good. The environmental sustainability is very high, as you can see from how the color fills all the way to the corner point that's labeled environmental sustainability. Whereas aluminum actually scores pretty poorly on environmental sustainability. You can see because the radar plot the color does not extend out to the end. But it's rated high on bulk process, by which I think they mean that you can make a lot of it at once. One of the things about aluminum is that people are so used to making it, and we have infrastructure, and we have developed methods to make, thousands or millions of parts made out of aluminum. We can mold it, we can twist it, we can cast it. There's so many different ways to process it. And what's really interesting to me is that, at least according to their analysis, 3D molded wood looks really good on all of these different properties. So in this figure, what we're seeing is really interesting. We're seeing on the right in the inset, you can see what it looks like for different materials to be bent. So this is the natural wood. You can see that if you bend it to about 180 degrees, it will definitely break and snap. Shrunken wood will bend and deform, and the moldable wood won't. And then we see that we're actually looking at scanning electron microscope graphs of what's going on, of what we're seeing, and we can see here that the natural wood, you can see this is the fracture pattern, and here's the shrunken wood. It looks a little bit different, but the moldable wood, you can see how it looks. It's interesting because the cell walls, or the cell wall structure for the moldable wood, is able to undergo compression at the inside of the fold, and at the outside of the fold, instead of just breaking, you can see that the vessels kind of open up again, and that gives it this moldability. So up to this point, we've demonstrated that the moldability of the wood, of the treated wood, is better than untreated wood, and you can do all kinds of cool things. And so they're doing more folds here in these figures. You can roll it up, as we saw in the video. You can twist it around something. You can make kind of these origami structures. What's really interesting to me, though, is that the moldability, or rather the foldability of the moldable wood, was actually compared head-to-head with the foldability of aluminum. And what's really interesting is that actually the moldable wood was, you could fold it more times than you could the aluminum alloy. And that's a surprise, really, because aluminum and other metals are known for their ductility, which is to say they can kind of be drawn or pulled. Even if you don't heat up a metal, you can often kind of like shape it into a certain shape. You can take a hammer, for instance, and you can cold work steel into a certain conformation or geometry, and it can do that because it's not brittle. But wood is really not thought of in those terms. So it's really interesting to see that they took moldable wood and they folded it 180 degrees 100 times, and there was no break. However, when they took aluminum, they folded it to 180 degrees, so they folded it directly over like that. And after only 3 times, it broke. So this moldable wood really is remarkable in terms of its foldability and ability to be, shaped in different ways. I would say that it still doesn't have some of the properties that make aluminum really excellent to work with. So for instance, while it might be superior in some ways in terms of its ability to be shaped easily compared to aluminum, one of the things that's great about it is that you can cast it. And so aluminum, you can melt it and then it's a liquid, and then you can cast it into any kind of shape whatsoever. Wood, you can't do that. Even moldable wood can't be cast or can't be blown into something with air pressure to form like a very specific and complicated structure. So then they did some kind of show-offy stuff, which is always fun to see. So they made the honeycomb structure out of moldable wood, and then they put a car on top of it, and it did just fine. So that's cool. So there are a couple of figures from the supplemental information that I wanted to look at. One of them is what it looks like, the preparation of a helical 3D molded wood. So the fabrication process of the helical 3D molded wood, in which the moldable wood is twisted around a rod, followed by drying to set the structure. And then they take the rod away. So this is cool, so it was flexible, it was moldable, you could twist it and whatnot. And then once you dried it, it's there in that shape. And it's just remarkable to see this. This is wood, it's gone through a couple of treatment steps, but nothing too terribly fancy. And by the way, this is one of the simplest synthetic processes that I've ever seen in any paper, especially to make something so remarkable in terms of its properties. So what they do is they say, this is it, this paragraph, this is all the information that you really apparently need to understand the synthesis of this really remarkable material. So they take a sheet of natural wood, and then they treat it by boiling it in water with sodium hydroxide and sodium sulfite for 48 hours. And by the way, these are like dirt cheap chemical reagents. This is like about as cheap as it gets. Sodium hydroxide is used all over the place, as well as in wood and the pulp industry, like making paper and whatnot, and as is sodium sulfite. This is super cheap stuff. Then they immerse it in water several times to remove the excess chemicals. Then they air dry it for 30 hours. And then they immerse it in water for 3 minutes to form the moldable wood. And then after they shape it, they then dry the wood at room temperature for 30 hours. So I will say it's time consuming. So if you wanted to actually make this a manufacturing setup, you'd probably want to experiment with, maybe doing things at higher temperature, or figuring out ways to accelerate this process. So they also did some mechanical tests of the strength. So for instance, you can see this is a stress strain plot here. It's a very common way to assess the mechanical properties like the strength, the toughness, etc. of materials. And you can see that the natural wood is just overall, it just performs much, much worse than the 3D molded wood in terms of the tensile strength. And then, so that's the pulling strength. So if you took a material and then you put a weight on it so that it was kind of like the weight was pulling down on the material, that's tensile stress. And then compressive stress is like it sounds, it's like compression, it's the opposite, and it's pushing down. And you can see that again, the 3D molded wood has better compressive material properties than the natural wood, though the difference is not as stark as it is in the tensile strength. They also compared in this figure B here, the tensile strength of aluminum with that of molded wood, and they also compared the specific tensile strength, and that's the strength normalized by weight. So in other words, divided by the mass of the material used. And so a lightweight, stronger material will have a higher specific tensile strength than like a heavy, strong material. And you can see that actually the 3D molded wood has better tensile strength than the aluminum. And then when you divide it by the mass of the two components, the 3D molded wood has much better specific tensile strength, which is just really interesting. So, again, as I was saying before, I don't think that this could stand in for aluminum in every application, because aluminum just has properties that the wood doesn't. Like the ability to be cast is such a big deal, and cast aluminum parts they're just ubiquitous. The last thing they did in this paper is they looked at the environmental friendliness of the life cycle analysis, and they took all of these different sort of environmental concerns, and then they considered that as compared to the strength. So it's like they normalized the environmental impact to the mechanical properties. So they're saying, so like for a certain unit of good strength for a part component, for instance, you can expect this much environmental impact. And they talk about acidification, which I'm not sure what they mean by that, then carcinogenics, ecotoxicity, fossil fuel depletion, global warming potential, etc. And they said in their analysis, the 3D molded wood beats the aluminum every time. I didn't go into all of their claims in detail, so I'm going to take it with a kind of a big grain of salt. But overall, I think it's logical that the 3D molded wood is probably more environmentally friendly than the aluminum approach, just because, again, the aluminum approach, you have to use really high temperatures. And at some point, the aluminum needs to be mined, which is environmentally difficult. It's actually mined as aluminum oxide, and then there's a number of very high energy-intensive processes to bring it into, aluminum metal. Aluminum metal is also highly recycled, so that's actually a point in favor of aluminum. But overall, it's pretty obvious that the 3D molded wood is more environmentally friendly because, first of all, you have to grow some trees, which is good because it, captures carbon. And then you process it kind of similar to how you process paper, pretty basic chemicals, sodium hydroxide, sodium sulfite. You use water. There's no crazy solvents like that could form volatile organic compounds to be released and give people cancer. And then you dry it. And that you wash it in some water, you mold it, and you dry it. It's pretty straightforward, and it's pretty, I think, environmentally friendly. So I thought this was a super interesting paper. I think it has a lot of potential. This technology is amazing, and I really hope that we can start seeing these materials show up in parts, maybe in car parts, which is wild to think about, these wood components being used in cars or aircraft, or maybe in buildings. That seems like a good application. So I'll be really interested to see if we can start to see some news of these materials start to be incorporated in actual products at some point in the future. Well, anyway, I hope you enjoyed the video. If you did, please go ahead and like and subscribe, and I hope you'll join me again in the future soon. Bye.